Okay, so our final talk for today is by Benjamin Gess, and he will tell us about fluctuations in conservative systems and stochastic partial differential equations.
Right. Yeah, thanks a lot. Thanks a lot for the invitation. Pleasure to be here. Yeah, so Jonathan invited me to speak a bit about non-equilibrium systems and their connection to SPDEs. This better. And their connection to SPDEs, and so this is a bit like maybe an excursion from what we have seen today, where we have focused on random matrices and random Schrödinger operators. So this is not what we're going to see here, but yeah, hopefully it's meant to be an invitation for you. And so I sort of take a very broad overview of a field and try to motivate the questions we're trying to ask and answer. And everything I'm talking about here, this is joint work with Ben Fairman, he's in Oxford, and Daniel Heidecker, who is a postdoc at Max Planck. And I've put actually the slides online, so if you want to recap something that was on a previous slide, you can find them already on the webpage and go back. All right. So what I would like to do is explain a bit. Sorry, something's not working. Yeah, it doesn't work. What's going on? Aha, okay. Good. Now it works again, yes. Alright, sorry for that. Okay, so what I want to do is I want to start with looking at interacting particle systems, and I want to like to explain how from the particle systems we go to conservative stochastic partial differential equations. Then I want to have a look at large deviations in this context of stochastic PDEs and lay out how this leads actually to looking at PDEs. So then we are leaving the realm of probability theory and entering just analysis, so just purely PDEs with irregular coefficients. And then I want to sort of close the circle and show how if you understand these kind of questions on parabolic, hyperbolic PDEs, you can go back and answer questions also on interacting particle systems that we started with. So let's see if I make it. Right, so I want to start with the interacting particle systems, and there are many choices actually that now you could consider. I'm choosing one here, the zero range process. So the viewpoint should be you look at now the microscopic level. So we consider reality to be a collection of atoms and they interact, and that's our perception of reality. And this is on this slide. So here I describe our toy model for the microscopic picture. And right, physically, of course, you would have atoms and then you have Newton's laws and they interact like this. This is too complicated for us in here. And in order to be able to say something rigorous, we look at the toy model. And yeah, so as I said, this is the zero range process. It's a particle process, so you have atoms, so you really see the individual atoms here. We put it on a grid, let's say with periodic boundary data. And yeah, the state of a process just means that you say how many particles sit at which point in space. Right? So the state of this microscopic world, it's just given by configurations that are just mappings from the torus to the natural numbers. And they indicate how many particles sit in slot K. Right, so far so boring because this would just stay stuck, and now we want to have dynamics on this. And the way we do this is by specifying two things. One is what is called a local jump rate function. This classifies the incentive that particles have to jump away. So the mapping, taking a number of particles and then giving you a real number, classifying the rate at which particles decide to jump. So in particular, choosing the rate function g to grow quickly, this would model on a microscopic level the incentive not to have too many people or particles around. Right? So you would diffuse more quickly and make more jumps if there are more particles in your box. So these would jump faster than the single guy here. All right, so this would just say how many jumps appear, then you would also have to classify where you jump to. So this is given by a translation invariant probability kernel. So this just specifies the probability to jump from box K to box L, right? And there are not so many assumptions around here. We are just assuming that, well, it doesn't really depend on the boxes, just on the distance you jump. And we assume, and there's an important assumption, that on average we stay stuck, right? So we don't prefer to go to the left or to the right, but on average we just keep stuck. And this is all we need. So given these ingredients, we can write down a generator for a Markov process, and then you can see that there exists a process which corresponds to this generator, and this gives you a continuous time discrete space Markov process. And this would now be the microscopic dynamics, which we accept to be our reality for the moment, although of course it's a toy model, right? And well, this is a stochastic object, so eta is a random function, and evaluating at t in box k tells us how many particles are in box k at time t. Yeah, and obviously this will be a random number because the jump particles make are random. Okay, now you could say I'm happy with this. I stopped working and worrying about theory because this is my reality, but well, that doesn't bring you so far, because if you have 10 to the power 10 particles or 10 to the power 6 particles, then this is not something you can actually realize. Even numerically, it's not feasible in big systems to simulate this, and even more systematically, you don't learn so much. You write it down, but then how effectively they behave, you can't read it off from the generator so easily, at least. Right, and this is now, of course, the principal question in statistical mechanics. How can we derive efficient, effective description of these dynamics? And one of the first things we would do is to try to look at hydrodynamic limits. So instead of looking through the microscope at our individual particles, we want to consider the reality to be a continuum, and a continuum which then evolves in time somehow. So yeah, stop looking through the microscope and look at the dynamics from far away, and then reality doesn't look like this collection of particles anymore, but it looks like a continuous object which changes in time, right? And the question is how to go from this microscopic picture to the macroscopic picture. And here now it comes into play that I've started with this toy model. So in this toy model, this can really be done, and we can write down what this, how this transition looks like precisely. So let's just introduce a mathematical expression for this picture here. We just look at the empirical density field, which just counts how many particles sit in which box. So we take a Dirac mass, put it on a box, rescale the boxes so that we stay on a unit cube all the time, and then multiply the number of particles. So the information you have here is the same as the information you have here, because particles were already indistinguishable here. Right, and the question is, when n goes large, where does this random measure that we have now identified on this left-hand side, what this converges to? And right, this has been done. So this is theory from the late 80s. A lot of people involved, citing here the work which is precisely doing this for the zero-range process. And what you see is that this random measure we start with, this empirical distribution, this converges to a deterministic function. Yeah, so this is of the type of a lower large numbers statement. And the important thing is that we can classify what this function looks like. Namely, it appears as a solution to a partial differential equation. And this partial differential equation we can write down, and everything in this PDE is given from the microscopic world. And apart from this being a nonlinear, so we would say a quasi-linear partial differential equation, this is something you would immediately expect to see. Because microscopically we had particles that diffuse around, so you would kind of expect to see some kind of diffusion equation. And this is still true here. But it's a nonlinear diffusion equation, and this is just brought in by our microscopic ansatz, where we already had a local jump rate function, which already allowed us to let the diffusivity, so the incentive of particles to jump, depend on the local number of particles. And this carries over to the macroscopic picture. And really, this can be really made precise, so we can compute what this nonlinear function is in terms of the local jump rate function, just we have to integrate it against the local equilibria of the system. Okay, so now this object I don't really introduce. The idea is that the microscopic picture, if you look at a large box in the microscopic picture, then everything averages to a mean density. And in these mean densities, you get invariant measures which look like this. And then you have to integrate against them to see the diffusivity on the microscopic scale. Okay, so now you could again say, now I'm happy, because instead of looking at this very complicated dynamics, mu n, I have derived one equation which now describes the limiting behavior of this system. And this I can study. So I just forget about stochastics and I do PDE theory, and well, in certain regimes, of course, this is reasonable to do this. But, okay, you lose something when you do this, namely because effectively what you are looking at, if you concentrate only on the limit here, is just the average behavior. Yeah, so the typical behavior of your system is something you would capture by looking at this PDE. But the microscopic, I mean the real dynamics, mu n, even if n is large, still has fluctuations. Right? This is still stochastic, it concentrates on a mean, but it's not equal to the mean. And these fluctuations, they can be important. Right? So they can be important, for example, because they can have a huge effect. Consider, for example, a technical instrument like a hard disk, which you access like 1 billion times, and 1 billion times it goes right, and you're happy with this. But then you still want to control the case where it goes wrong. So the probability will be small, but still the effect will be large. So caring about rare events is something of quite practical importance. Another way to look at this is when you look at long-time behavior, so you want to understand the long-time behavior of a microscopic system, then you know that in the long run, actually the dynamics of a stochastic system, it's dominated by the rare events. Because the rare events are the events that send you from one potential well to the next potential well. So in the long time behavior, if you really forget about the fluctuations and look at only at the mean, then you might make really wrong prediction. So this is one aspect where just looking at PDEs falls short. Another problem with this is that, okay, this is just a convergence. Right? So it's true when n goes to infinity, you end up with this concentrated measure on a Dirac mass. But you make an error when you replace this by this guy. Right? And the size of the error you can quantify. This is just by writing down or developing a central limit theorem. This tells you how big the error is in between mu n and rho bar. And it will be exactly n to the minus 1/2, like you would expect from a central limit theory. Right, so saying that I replace my microscopic model with a solution to a PDE, it means that I accept this error. And right, if you talk about a very large system like an ocean, and you want to sort of model the geostrophic flow of a fluid on the level of an ocean, then this is so small that you would be happy just with another Stokes equations. But if you are in a setting, for example, you have a thin film of a fluid, and you want to study how it tears up into blobs, then n is large, but not so large that this is negligible. Right? And in this setting, then it becomes questionable whether it's a smart idea to replace mu n really by the deterministic object rho bar. And so from this, we could say, okay, now, well, but we still need to simplify our system, so we cannot work with mu n. So what should be a different simplified object that describes on a continuous level to a certain degree mu n, but does not have these problems that we lose information about large deviations and we lose information or we make a big modeling error. So the picture to have in mind here is that instead of going from the microscopic scale to the macroscopic scale, as I indicated it here, what we're actually interested in here is sort of a mesoscopic region here, where n is not yet large, so large that we see just a PDE, but it's already kind of large so that we see some averaging behavior appearing. And this we introduce next. So we introduce this mesoscopic scale, and I'm trying to indicate here that what we should see on this mesoscopic scale is already something of this mean behavior. So it already sort of takes the form of this guy, but fluctuations are around to a degree which do make a difference to the dynamics. Right, okay, so I can write down a picture and maybe give an intuition of what this mesoscopic picture should look like, but then the question is, okay, but how do you write down an equation for this? And now I just sort of throw it at you and justify it a posteriori. So this is precisely where conservative SPDEs enter the game. So they take a very particular form. The first part, just looking at this part, this is just the same as the large number that we saw. This is just the nonlinear diffusion equation from the last slide. And now we correct about this nonlinear diffusion equation by introducing a new perturbation to this deterministic PDE, which is a random fluctuating term. And the important point here is that I don't just add something here, right? I don't just add an unknown term, but I add something very specific, and I should justify why this I believe to be the right correction to the deterministic object. And maybe have a look at this. So the structure of the fluctuation correction is that you have a divergence. I put everything in 1D here, but it's not important. I could write it in multiple dimensions. The important thing is that this is a divergence of a function of the solution, and this is typically a nonlinear function. So if you were just to look at this part, you would say, well, this is a conservation law in PDE theory. But then the interesting thing is that it directly interacts with noise, xi n. So this is a noise term, and now this is not like in the talks we have seen so far. It's not just a random object in space, fixed for all times, but this is something which is wide in time. So in each instance in time, it's independent. Okay, so this is a fluctuation correction, and xi n, now if you want to be a bit more precise, it's a noise which is correlated in space, because we had, in the beginning, we had a grid model, and the noise or the action of the particles was independent on each of the grid points. And it's decorrelated in time, so it's wide in time. And one can write it in various forms, so if you have seen SPDEs before, then often it's just expanded in terms of a sum of Brownian motions. But it's not so important for what I'm telling you here. For the intuition, it's just important to know, okay, now we have this kind of noise entering the picture here, and we are not dealing with partial differential equations anymore, but with stochastic partial differential equations. All right, but why did I choose it in this fancy way? And to justify this is a bit of, you can take different directions to see why this is the right form. The first one is more coming from physics. So this is a generalization of what is called a fluctuation dissipation relation, which relates, as the name says, it relates the amount of fluctuations you have in a system, so this guy, to the amount of dissipation you have to this guy. So it sort of prescribes how a fluctuation would look like once you have fixed the dissipation. Right, and this one we already know what it looks like. Okay, but I'm just saying words here, so rolling this out and making it precise is a bit of work, and it relates to actually interpreting a PDE, so the mean behavior as a gradient flow on an infinite dimensional Riemannian manifold. So like this auto gradient, auto interpretation of a nonlinear PDE. And then the fluctuation correction is really writing down the Fokker-Planck equation in this infinite dimensional Riemannian geometry. Another way to look at this is that you introduce noise in such a way that you see the right Gibbs measure appearing in the mean dynamics. And so this is an analogy to what you would do when you write down an overdamped Langevin equation for SDEs. You know what the invariant measure should look like, and then you add noise in the geometrically correct form so that the Gibbs measure is given by the form you expect it to have. Right, so this is coming from physics, but I want to convince you of this fluctuation correction more from a mathematical perspective. Namely, you can just formally check that when you perturb your PDE in this way, then you get the right predictions. In the sense that we can check that the fluctuating field rho n here, it satisfies the same large numbers, the same central limit fluctuations, and in particular the same large deviations behavior as the original system. So we started with our microscopic system UN. I've now written down formally a continuum object which is meant to show the same fluctuation behavior as the microscopic system. Yeah, and that means that it should satisfy the same properties down here. Yes?
Just a question. When you say it satisfies the same things, it's always integrating over macroscopic functions? In what sense, so when you say CMPs, after you integrated over the macroscopic function?
Yeah, I'll explain. Yeah. And then maybe you ask again, and let's see if I explain it.
Okay, thank you.
Okay, so let me look at this. So we start with the large deviations. So I want to check that the large deviations to this guy formally are the same as the large deviations for zero range processes. Thereby I mean path space large deviations. And well, informally you can do this. So let's just look again at this stochastic corrected PDE. And you see there's a factor n to the minus 1/2 in front of the stochastic correction. So if I drive up n, look at n tending to infinity, it means that I see this factor going to 0. So I'm in the setting, roughly speaking, of Reitlin-Wenzel and path space large deviations. Just with the additional difficulty that we're not looking at SDs, but at SPDEs. Still, formally, I can make a computation, and now it gets very risky because I'm speaking about an object where we don't really yet understand what it is. And I'm pretending now that I can apply the contraction principle from large deviations. But okay, we do it nonetheless. Okay, so I want to look at rare events, meaning that I want to classify the probability that my fluctuating system rho n looks like a given function rho. And if this is not the typical realization, then this should be a very small probability. It should decay exponentially in n, and the exponential rate of decay should be classified by the rate function I. Okay, large deviations. So the interesting object would be the rate function, right? And we want to see that the rate function we get formally from the SPD is the same rate function that we know to be true from the microscopic world. So let's pretend that the solution to this SPDE is a continuous map of the noise. If this was true, then we could apply the contraction principle from large deviation theory, and this would tell us, well, okay, if you have an LDP for the noise you plug in, you have a large deviation principle for the solution to your equation. Yeah, and the rate function, it would just be the infimum over the pre-images of f of the initial rate function you have for the noise that you plug in. Okay, yeah, this line is really just the contraction principle. I've hidden everything in the notation, and now we can just expand the right-hand side here because these are concrete objects. So what should this be? We will have to plug in the rate function of this guy, so the rate function of something which is space-time white noise. This is now space-time white noise because when n goes to infinity, the noise we plug in here converges to space-time white noise. Right, so this one we know, the rate function of space-time white noise is just the A2 norm. So here we have the infimum over the A2 norm, and then we take the infimum over the pre-image of f. So we take f, but don't plug in the noise, but a control g. Meaning that up here we have to replace the noise by a control. And otherwise, rho should be then a solution to this equation. So end up with a variational formulation, right? Just this line re-expressed in what these objects mean. And I get a rate function of this type. It's a variational form of minimizing the cost of a control g, where the controls g are chosen so that the given function rho becomes a solution to this PDE. Right. So the important things here is that you see in the precise form of the rate function that I get out from this, I recover the structure of the SPDE or SDE or whatever that you started with, because the precise structure of this correction operator, this is still present here. We've just replaced the noise by a control, but otherwise the structure of the correction is precisely the same, which tells you that if you want to correct your partial differential equation in such a way that you get this rate function out of it, then there is no choice, but you have, because you know what this guy looks like, you have to correct it in this way. So in this sense, it uniquely classifies how a fluctuation correction to the SPD would have to look like. Okay, so in this sense, the large deviations, and now very shortly look on the question of the approximation error. Again, one can make a formal computation here. I write down the SPDE and I look at the central limit theorem now. So in the sense that I want to expand my solution to the SPDE in terms of the intensity of the noise. So I want to look at rho n, subtract the mean behavior, rescale by n to the 1/2, and then see that it converges to a Gaussian Y1. Okay, that would be my central limit theorem. So this is on path space. The topology, this is a much finer question. So everything I'm saying now is very informal. So you would have to think first how to make sense of this equation. Right? So, but I can answer this. One way to do this is, the weakest form would be you first choose a test function and observable, and then look at this under the observable.
The reason I was asking, so that your test function is macroscopic.
Right, yeah.
Okay, so
Yes.
because you call it between macroscopic and microscopic, so there's another way you could do it, which is to take mesoscopic test.
Right.
But that's not what.
Well, I call this model mesoscopic, but then I'm comparing things here on a macroscopic variable, right? But this is still a mesoscopic model, and so far that you regenerate the same large deviation behavior. Right, so I can expand these two objects. I can take my true system mu n, and I can look at the central limit fluctuations about this mu n, right? So I subtract rho bar, I rescale things, and then I see that it converges to Gaussian. I can do the same thing for the SPD, and I see that the Gaussian fluctuation that I expect to come out of this, they are the same ones. So this tells me that when I look at the distance between this fluctuating object rho n and this fluctuating reality mu n, then the first two terms cancel. So you don't see, like if I compare mu n just to the deterministic object, I would just see n to the minus 1/2 decay, like this was the thing we saw on the second slide. But if I compare mu n to rho n, then both two first terms cancel and I see a decay of n to the minus 1. Yes, and this way you have decreased the modeling error in this sense. And this one can see, this now it depends a bit on the precise system you look at. So this kind of question on the CAT, this you can prove for the symmetric simple exclusion process, for example. All right, so yeah, this was just like a motivation of justifying that this ansatz for this SPDE is the correct one in the sense of reproducing this kind of fluctuation behavior. Now I have not said anything about the math difficulties here. Okay, so the first thing you would have to face is you would have to make sense actually of this object, and this is not easy. So point here I didn't stress yet is that, well, this fluctuation correction, you see a square root popping up here, right? So even if you look at the linear setting, so when you just have a linear heat, mass diffusion equation, so this is just the heat operator, then in the fluctuation correction you see a square root of the solution. So you're always facing nonlinear equations and you face singular coefficients in the sense that, well, the square root not being Lipschitz continuous. So there are issues with this, and well, this has been worked on since 2013, initiated by Lyons, Bertam, and Zouganides, and then we have continued this development of the theory, and by now there's an existence theory which allows you to speak about what it means to be a solution to these SPDEs. So there is a unique solution under conditions on the nonlinearity topic. Once you have answered this question on the well-posedness, you can approach this qualitative behavior. For example, you can look at large deviations as I indicated, and we have done this. So the path-space large deviations, which formally I derived 2 slides ago, we have derived in this work with Ben Fairman. There are other works in this direction, going back to Mariani, for example. And also these kind of expansions and central limit theorems have been investigated by a number of people. So there's one case where this can be made precise. This is the symmetric simple exclusion process. And the other cases are in the linear setting, where you basically are looking at Brownian motions that are independent and walking around. Right, so, but there are many things that need to be developed. So these are just examples where we can do it, but the principal ansatz is more general, and in many cases we don't know yet how to make these things work. And I focused here on one example of the zero range process, but well, the same thing you see in fluid dynamics. You see this appearing. You see it appearing in machine learning. When you look at stochastic learning algorithms, then you can also look at very large networks, and you sort of see the same problems in principle, but there you have non-local PDEs. So again, mathematically, there are many challenges left. Right? But the viewpoint is always the same. It sort of follows these lines of trying to correct the fluctuations to go to capture right large deviations and right central limit theorems. Okay, so well, this was the initial motivation to go from particle systems to conservative SPDEs. So maybe you've now understood like why this type of correction is the correct one. And now I'd like to explain a bit of the connection between looking at large deviations and how looking at large deviations leads us to asking questions in PDE theory. So you start with a probabilistic question, but then you end up with a purely analytic question in the end. There's a question.
I mean, you chose CN to be white noise, time white noise. Why that? Is there any physical justification for that, or is it just because you know how to solve this equation and it turns out to give you the right fluctuations, right? And in which case you could replace it by some other quantity giving you the same results.
Right. So one intuition, so one reason is that, but I sort of didn't explain this, when you write down, okay. So the PDE part, this I can interpret as a gradient flow. So I can write down an energy for this guy, I can write down a Riemannian metric, and then this becomes of the structure of having a Riemannian tensor acting on a gradient of some energy. Right, and then I can say, now I want to look at the fluctuation correction to the system, and the way I should correct this is that the formal Gibbs measure I get by identifying the energy, like e to the minus inverse temperature times the energy, this should be my invariant measure to the fluctuation corrected object. If I do this, then the way you have to correct it is precisely this guy, because the structure you see here is actually the square root of the Riemannian tensor acting on space-time white noise. And that gives you formally the right Gibbs measure in the end. And well, there you put in space-time white noise, so this would be consistent then with this choice. All right, so the next jump now to PDE theory you can also follow if you you're not interested in SPDEs at all. So this appears also when you look at just particle systems. So yeah, let's keep looking at the zero range process, and now I'm asking again the question about ray events or large deviations. So I want to understand the probability of this system UN looking at a given function rho, and I want to understand or prove that asymptotically for n large this behavior is true. Right, of course there I'm writing things very informally, so be a bit more precise. This consists of two things typically. You show upper bounds and lower bounds in this large deviation principle, and the way to do this is to formulate this is then that you say for closed sets or closure of open sets you have the upper bound, and for open sets you have the lower bound, and you want that you get the infimum here over all the fluctuations rho in the set that you look at. Okay, so this is the same formulation. If you replace this by a point, you're sort of back here, but this is the rigorous or more rigorous way to write it down. And yeah, we want to understand this for the zero range process, and this has been done. Yeah, of course, this is nothing of the slide is going back to me, but this is theory now from the late 80s. I cite it on the next slide. And yeah, you can see what the rate function for the zero range process should be, at least in this rough form. And what you get again is it turns up in a variational form, so you get an infimum over some cost of a control h, where h now is a control to, again, a PDE. So h has to be chosen so that rho becomes a solution to this controlled PDE. Yeah, but now it's important that this is a different PDE from what we guessed looking at SPDEs. In SPDEs, I called this a skeleton equation, and there we had here phi to the 1/2 appearing, making this a nonlinear PDE, even in the case where phi is just the identity map. This is different, so in the classical theory, if you look into Kipnis and Landin's book on interacting particle systems, for example, you will see this form for the rate function. And I call this a controlled Fokker-Planck equation because if phi is the identity, this is really a controlled Fokker-Planck equation. And yeah, just some bookkeeping. So this one looks like a weighted H1 norm for the control H, and I call this weighted H1 norm by this notation. All right, so this should be the rate function you can guess that should capture the large deviations of the zero range process, and now this has been considered. So I'm pointing here to Kipnis, Oller and Baradan in 89 and Benoit Kipnis and Landim in 95, and there they have sort of realized the typical way, going back to Baradan, how to prove large deviations for these kind of systems. And they have shown separately upper and lower bounds. Yeah, so first of all, you prove that the upper bound for rate function I, and then by a different argument, you prove the lower bound. And yeah, in principle, everything looks good here, but there's a subtlety, namely that the lower bound rate function is not known to be identical to the upper bound rate function. So these are different steps in the proof, and you get out potentially different rate functions from this. And well, okay, J is not just anything, but this lower bound rate function J is really the upper bound rate function restricted on some small set, like a set of nice fluctuations. And then for free, you can always take the lower semi-continuous envelope. And this is what you can prove. This is the rate function you get for the lower bound. I should tell you a bit like what is the small set. So what you have to do is you restrict to fluctuations, rho, which can be written again as a solution to the controlled Fokker-Planck equation, but with a control H, which is supposed to be nice. And this is something which is not generic, right? So I just assume that I can write rho as a solution to this equation where H is a C13 control, so a regular object. And for generic fluctuations, this would not be right. There's no reason why C13 pops up. Like if you look just at the rate function, there was some H1 norm appearing maybe, but nothing strong like this. But in the proof you need this, because you make a change of measure in the microscopic setting, and then you pass to a limit. And well, if you have no regularity here, then you're facing generators with very irregular coefficients, and it's really not clear how to make the argument work otherwise. Right, now you may think, well, this sounds super technical. Maybe this is just because you don't work hard enough, and well, I don't think that's true. So there are many instances where you precisely fall into this category, where you have large deviations, upper bounds, and lower bounds, but you don't know that they coincide. And there are a bunch of examples. So also in more recent works for fluctuations around Boltzmann, going back to these authors, you can see precisely the setting that you have lower and upper bounds, but you don't know that the rate functions coincide. And interestingly, for the Boltzmann equations, there were counterexamples. So for the rate functions identified in this work, Daniel Heidecker could show that they're not the same. So maybe you have to improve the upper bound, and then you find something matching, but at least it's not a simple problem. And yeah, if you have a situation like this, I would call it a restricted large deviation principle, just to make clear that where we have upper and lower bounds, but we don't know that they coincide. Okay, so let's go back. So what are we missing? So in order to see that the lower bound rate function j is the same of the upper bound rate function, I would have to show that when I take my rate function, I restrict it to nice fluctuation and then take the envelope, that I get back to the initial function I. Right? I have to show that j is equal to I. Okay. Let's see what this means. I have to identify the lower semi-continuous envelope here. Okay. Now we're really looking at an analytic question, and this slide is just going to take this line and expand it back to what it initially means in order to understand what then we have to prove. So the question in identifying the lower semi-continuous envelope of a restriction of a rate function is always, or the hard part is the existence of a recovery sequence, meaning that I start with an arbitrary fluctuation with a finite rate, which just means, remember this rate function was given by a variational principle, so this to be finite just means that I have to find some control h so that my given fluctuation rho becomes a solution to the Fokker-Planck equation. If I have this is equivalent to the rate function being finite. So this is just an arbitrary given fluctuation rho with finite rate, and now I need to find nice fluctuations that converge to this given fluctuation so that the corresponding rates converge. If I can prove this, then I can identify the lower semi-continuous envelope. And okay, now I just keep expanding. So what does it mean? So rho epsilon being a nice fluctuation, it meant that I can write rho epsilon as the solution to a controlled Fokker-Planck equation, but with respect to a regular control h. Plug this in. Okay, so I need to find regular controls so that the corresponding, so that I can write rho epsilon as a solution to this controlled Fokker-Planck equation. I need to show that the corresponding rate functions converge, and I need to show that the rho epsilon converges to rho. And nowhere there is probability now, right? So this is now a purely analytical question, and it doesn't look absurd, at least, because now if you read it from the bottom to the top, what it means is that, okay, I look at solutions to PDEs, they are driven by a control. This control in some sense converges to a limit, and I want to see that then the solutions converge to the limit solutions. Okay, on a very informal level, it seems like, okay, maybe it should be true. But the difficulty is that in the limit, this PDE, this is not a nice object, because here we control it with the generic control H, and there's no regularity for this guy except that it's an weighted H1 norm. And I take the derivative of that guy. So this guy is just something like, what, integrable, but nothing more. So now I'm looking at a partial differential equation, which is of the type of being parabolic, hyperbolic, where the hyperbolic part is subject to irregular coefficients, and drastically irregular coefficients. And on this level, you don't have a priori any well-postness theory. And this makes this hard to really prove this, and this is why, well, for the zero-range process, this question of the full large deviation principle was open since this work in the mid-90s. All right. Yeah, so this way we have made the step now going from interacting particle systems or conservative SPDEs to PDEs with irregular coefficients. Now I have to look at the watch. Yeah, so maybe let's compare this for a second. So we already had seen the rate events for the conservative SPDE, and I told you the rate functions are the same. Now you might wonder, is this actually true? So remember this from the SPDE world, the rate function that we guess actually looks like this. It's a small trick how to rewrite each of these expressions into one another. But I want to stress that coming from SPDEs, actually the sort of natural object to look at is this form of the variational rate function. And this is actually useful. So there you can learn something from looking at the SPDE analog of the zero-range process in understanding the large deviation principle for the initial process itself. Namely, the SPDE suggests to look at the rate function in this variational form instead of the variational form controlling the Fokker-Planck equation. And this is something which mean, if you were not looking at the conservative SPDE form here, it would look absurd, because the Fokker-Planck equation is a linear equation. This looks sort of nice, whereas the skeleton equation is always nonlinear and always looks ugly, because you're always facing like a square root term here. So you wouldn't typically say, okay, now I'm looking at this object and study it. But the point is that really, in the end, it turns out that when you're facing these kind of stability questions for PDEs, they are better behaved on the level of the skeleton equation than on the level of the Fokker-Planck equation. And without this realization, I don't think, well, I mean, yeah, people did not succeed in being able to prove the stability to these equations. Right, and here I'm giving the sort of back of the envelope computation that the rate functions are the same, so you can start with the Fokker-Planck equation, and it's really trivial rewriting. I write this as 2 square roots. Then h being in a weighted h1 norm just means that this is precisely a2. I call it g, then I'm reaching the skeleton equation, right? So they are formally really the same objects. Yeah, but mathematically, when you do the analysis, then it turns out that the skeleton equation is more handy. But still not easy, of course, right? I mean, this is a super ugly equation, because still you're facing a hyperbolic equation with irregular coefficients and then driven with an inhomogeneity g, which is just an L2 function. So actually, with experience from PDE theory, you might be skeptical whether you can prove something there. And yeah, this is maybe something one can now try to guess. So I have to prove well-postness to these kind of equations for g being an L2 function, and well, how difficult is this actually? Right, and a good idea to start with when you ask this question, so you're facing sort of a new form of PDE and it has irregular coefficients and you want to understand how difficult it is, a good a test case is to look at the rescaling, to sort of look at the local behavior of solutions to the PDE and understand how they behave locally. And this is what I want to start with, looking at PDEs now, namely with the question, how difficult should it be? All right, so what I did first is I tried to come up with a priori estimates which actually hold up. So I test this equation in LP spaces and try to see whether I can prove any a priori estimate. And when you do this, you fail. So that doesn't work. But of course you don't know, well, am I not trying hard enough, or is there something difficult going on? And to understand what is going on, we do rescaling ansatz. So let's look at the case where the nonlinearity is really given as a power of the solution. Yeah, and if you want to keep it simpler for you, just take m equal 1. So look at the heat equation. Then, okay, the skeleton equation takes this form, so you have a heat equation here, but you always have a square root in here. And now you plug in coefficients g in some LPQ space. And you want to know, well, if you can expect regularity from the solutions or not. And then the way to do this is to rescale the equation in order to zoom in and see the local behavior of solutions. And then in this rescaling ansatz, what you need to see is which of these terms dominate. If this term dominates or if this term dominates. If on local scales the diffusivity dominates, then you expect that your solution also has some regularity. Because this guy, it will give you some regularity. If on local scale it dominates, then this should be present in the solution. Because regularity is a local scale solution property here. If on the other hand this guy dominates, then you have no chance. Because then on local scales, this equation, it will look effectively, or essentially like a conservation law, and the conservation law produces shocks. So there will be no regularity. And yeah, therefore, with the rescaling ansatz, you can make a sort of definite conjecture, at least, of what should happen. And what you can see here is that neither. So it's sort of good and bad news. So this is not super critical in the sense that when we zoom in, it's not the case that the hyperbolic part would dominate. Then we would be dead. But also, unfortunately, it's also not the case that the parabolic part dominates. but in the case that we're interested in, namely G being just an A2 function, it's precisely critical. So you would call this a PDE with critical coefficients, because regardless on which scale you look at for this PDE, it's always the case that there's a competition between diffusion and transport. So you gain nothing by looking at local scales, basically. Right, and this also explains why when you look at AP estimate it fails, because when you now do this rescaling in LP spaces, like you let your initial condition be in an LP space, then you see that also R equal 1 is critical and all higher order spaces are supercritical, so there nothing should be expected. Yeah, so this tells you, well, okay, maybe you shouldn't give up because it's on the critical line, but maybe also you should expect that it's not super easy to prove. Another way maybe to approach this is to look at literature. So, I mean, PDEs with irregular coefficients, this has a long history. You can compare it to the works by Lyons and Lebris, which is sort of expanding on Di-Perna-Lyons theory from the early 90s, and actually then there's a long history of people looking precisely at these kind of parabolic, hyperbolic equations with irregular coefficients, and they've pushed the theory of Di-Perna-Lyons to these settings, but always under the classical assumptions of Di-Perna-Lyons. So what you always need in this theory is that your coefficients G have some kind of differentiability. So Ambrosio has pushed it to be V functions, but then still you need some kind of differentiability and boundedness of divergences. So there's a whole field working on understanding this kind of Lagrangian flows under these conditions and so on. But for us, you see, it does not help at all, because our coefficients are just L2, and you can do nothing about this. This is not just for a mathematical challenge that we look at L2 coefficients here, but this is what comes out of the rate function. This determines the regularity of G, and it's just L2. So this doesn't really help, and again, therefore you also see, well, it should be sort of difficult to make this work. Right. So this is what we do, and now this part is the part with Ben Fairman, one of the works I cited in the first slide. And what is done, there are three main ingredients in now proving well postness to these PDEs. The first one is develop a priori estimates that actually work. And I already told you that LP estimates fail, and what saves the day is looking at entropy dissipation estimates. And this, in a sense, is not super surprising. If you come from the analysis of the zero-range process, then also there you would look at relative entropy estimates or entropy estimates, and you would already use there that they can be closed. And similarly, we see it on this level. The more difficult part is to then prove uniqueness. And this really amounts to developing a nonlinear extension of the classical Di-Perna-Ambrosio Lebris theory to this world of nonlinear PDEs. Because we move from the Fokker-Planck equation to the skeleton equation, which is always a nonlinear object. So this means that you would prove that any weak solution to a PDE is a renormalized solution, and then one has to prove that renormalized solutions are unique, which is immediate in the linear setting, but which is still difficult in the nonlinear setting, and there we extend theory by Benoit Pertam, so-called kinetic solutions, and combine them with the theory of Di-Perna-Lyons. Okay, now these are basically just buzzwords, because every step here I could talk about a long time, which I don't have. Right, so maybe let's close up to what we get to in the end. So now I'm jumping about the details of these three steps. 3 slides. So in the end, all of this works. And what we developed, motivated from large deviations for particle systems, is a well-postness theory to parabolic hyperbolic equations with irregular coefficients G, which are precisely L2 coefficients. Although it looks like in the beginning that may be very difficult because of criticality, in the end it works. And we can prove that indeed also we have this kind of stability that the solutions to these equations, they depend continuously on the coefficient g. And now you remember that when I talked about the closure problem of the rate function, this was precisely what we had to prove. To prove that when the controls converge, the solutions converge. And this we get. So this is a complete theory for this, and we can then use this, and this we did in a follow-up work. This is with Daniel Heidecker, so we can go to the zero-range process, look at the rescaled zero-range process, and by using this PDE theory, then prove a full large deviation principle. Yeah, full in the sense that we have matching upper and lower bounds, which is quite rare after all. So in this symmetric simple exclusion process, you can do it because the rate function is convex. You can use convexity to sort of identify upper and lower bounds. There's, well, an example in TASAP, so totally asymmetric simple exclusion process. In the slower rescaling of the rate function, you can get a full large deviation principle, but there are not so many more examples of where you can close this. Yeah, and now we have one more, the zero-range process. Also there we have now a full understanding of this. All right, and yeah, so these are the two references associated to what I've shown to you. We have sort of closed the circle now from going from PDE theory back to the interacting particle system. With this, yeah, I close. So thanks for the attention.
Thank you very much. Questions or comments?
So I had another question in the same, well, I don't remember the slide number actually where the equation was on, but at some point, right, it seems to me that to understand that the correction, right, the a priori form of the correction that you're using is the right one, you use knowledge of the rate function for the large deviation principle, right? Because I think you stated this this way, right? But the thing is, if you already know this rate function, right, for the microscopic large deviation principle, what's the purpose of actually using the approximation? I mean, if you already proved large deviations on microscopic, I mean, if I understood the whole plot completely, right, the idea is I don't know how to solve the microscopic problem, right? I try to replace it by some mesoscopic problem that I will know how to solve, which will actually give me information about the microscopic problem. So if I already know the rate function for the microscopic problem, right?
Yeah, I understand.
This is something that
so you don't add new information in this sense. So
yeah,
so the large deviation principle, if you know the microscopic problem and you know the large deviation principle for the microscopic world, then you know the gradient flow structure of the PDE. And the gradient flow structure of the PDE, it determines the fluctuation correction. So in this sense, there's a one-to-one correspondence in between gradient flow structure, large deviations, Fokker-Planck equation, and SPDE. So the point you're making, or the question you're raising then is, should I not just look at the Fokker-Planck equation? Why should I look at the SDE? So this would be the analogy if you think about finite dimensions. And my answer would just be, okay, when you look at the SPD, you have different methods, you have different ways of thinking about these objects, and sometimes this leads to new insight. And I would say that we've seen like one example here, because the form of writing down the variational principle for the rate function, this is something which appears very naturally when you look at the SPD, and also naturally when you look at the gradient flow structure. But it does not appear naturally when you look at the particle system. So there you see this controlled Fokker-Planck equation. And because you didn't see the structure of the skeleton equation before, I think this is also one reason why for a long time this could not be solved. So there you have really gained some mathematical insight by following this.
Mesoscopic number says, is there a chance that, so then you get a different equation? Is there a chance that this mesoscopic point of view?
So, yeah, I mean, I didn't try it, so I'm not sure if I can really answer it on the spot. I mean, you can go higher in the expansion in n, and maybe this would give you some information on a more mesoscopic scale, but then you would have to also correct your SPD to higher order. So I mean, I could match. I mean, for example, you could match if I don't want to go back all the time, but so now I match just the large number and the first order expansion. I could write down the higher order Edgeworth expansion of the particle system, so the higher order expansion of the generator, and I could try to match this with a continuum object. So this would give you a more precise matching, but it would mean that you would have to write down a different SPDE, because you get higher order corrections. Then you get sort of fourth order correction, for example, and then you would see a different SPDE appearing. But I'm not sure if I captured your questions. Yeah.
Well, if there are no more questions or comments, let's thank Benjamin again.